welcome everyone again. This is our fourth webinar. Today we have our guest speaker, Professor Niklas Boers, so my boss. And we have also people in this audience who are new perhaps to our webinars. So I will give a short introduction to our speaker today. Niklas Boers is a professor of Earth system modeling at the Technical University of Munich, and he is also he leads the future lab called Artificial Intelligence in the Anthropocene at the Potsdam Institute for Climate Impact Research. He is also the lead coordinator of this Horizon Europe project called ClimTip, which we are part of, and we focus here on understanding and predicting climate tipping points. So Niklas's work focuses on complex dynamics of the Earth climate system, and particularly looking at extreme events and critical transitions, or so-called tipping points, such as the potential collapse of the Atlantic Ocean circulation, the dieback of the Amazon rainforest, or the destabilization of the Greenland ice sheets. Following his PhD in theoretical physics from the Humboldt University of Berlin, Niklas conducted his research on theoretical Earth system dynamics at several well-known institutions, including the PIC in Potsdam, which I mentioned, the ENS in Paris, the Imperial College London, and the Free University of Berlin. Throughout his career, he has received numerous accolades, including the Outstanding Early Career Scientist Award from the European Geosciences Union in 2021, and Niklas has also been awarded the Brandenburg Postdoc Award in 2019, a Freigeist Fellowship from the Volkswagen Foundation in 2019, and a Fyodor Linin Fellowship from the Alexander von Humboldt Foundation earlier. Welcome, Niklas, and the floor is yours.
Thank you so much, Kurt, for that kind introduction, and welcome everyone. So I'm essentially, as you probably noticed, I'm chipping in for Maya, who unfortunately couldn't present today because she's ill. So hopefully a speedy recovery. So I'm going to just give an overview of our recent work on tipping points, climate tipping points. Most of this as still work from TIPES, the project that preceded ClimTip, but also some recent updates that are already part of ClimTip. So it's going to be rather of an overview. I'm not going to be able to go into a lot of detail, but please feel free to ask questions, of course, and I'm happy to take them afterwards or in between, really, as you like it. Obviously, questions of understanding should be asked right away, otherwise it doesn't make sense. All right, so let me start and get right into it. I have two very, very short parts, which is anthropogenic climate change. That's going to be just 2 slides as a sort of motivation. Then I think it's only 1 slide on the paleoclimate evidence. And then the rest, I will spend the rest of the time we will spend to discuss the risks of future climate tipping. So this figure most of you have seen at some point. It's from the Summary for Policymakers from the most recent assessment report of the IPCC. And you see the evidence that temperatures have increased. On the left, you see this from reconstructions and observations, so the famous hockey stick curve for the past 2,000 years. And on the right, you see, again, the observed global mean temperature trend in black, starting in 1850. And you see the simulations that with the Earth system models and climate models that include both the human and the natural forcing, greenhouse gas forcing, and so on. And you see that the models do a good job in reproducing the increase, whereas if you take the models and exclude the human forcing, then you basically get a straight line with some wiggle around it, but without an increase, sort of attributing the increase in temperatures to the anthropogenic emissions. So spatially, and I still think that most of you have seen some variants of these figures. So we see the observations, the observed change per degree of global warming as a spatial distribution on the top left. You see the corresponding simulations on the top right. Pretty good agreement, except for this one spot south of Greenland that we will talk about, the warming, whole cooling. Yeah, I always mix this up, but yeah, okay. So, and then on the bottom, you see the simulated spatial distribution of warming for different degrees of global average, 1.5, 2, and 4. What becomes immediately apparent is that the Arctic becomes much warmer, warms much faster than the rest. That's Arctic amplification, which is a concern because some subsystems that we think might be rather sensitive compared to others are situated, are sort of dependent on the temperature evolution in the Arctic. So these are different projections depending on different scenarios, emission scenarios, land use change scenarios, and so on, for the time period from so the historical record in black, and then the projections starting in 2015 until 2100. And as you probably all know, so I mean, there's not high likelihood that we'll manage to get one of the blue lines, but rather, I mean, we can probably just hope for the orange and hope that the red won't happen. But that's sort of the range that's possible and that's ahead of us. And in terms of impacts, I'm only going to show you this one plot still from the AR6 for the global mean sea level rise, which doesn't seem to be dramatic up to until 2100. But of course, all of you know that there's a lot of committed sea level rise due to the warming that we are causing because of the inertia, in particular because of the inertia of the ice sheets. One thing that should be emphasized is that all these estimates in the IPCC are generally not including strong instabilities. So there is one sort of storyline approach, and with the dashed line you see under SSP 8.5, if you include ice sheet instability, and I think this mainly comes from the Western Arctic ice sheet, then there could even until the end of this century already be a sea level rise of more than 1.5 meters, which then would be substantial and quite dramatic for the coastal regions. But actually, if you just zoom out a little bit and look at how this looks if we go to the year 2300, which I would say I would really, I mean, yeah, I like to argue is still a time scale that we should feel responsible for, then you can't even rule out 15 meters of sea level anymore, in particular if you include any instabilities. So the gradual, still, I mean, of course, extreme and fast, but still gradual increase in greenhouse gas emissions and corresponding temperature increase. The concern that this has raised is that there could be subsystems of the Earth, like the polar ice sheets or the Amazon or the Atlantic Ocean circulation, that might respond abruptly. And of course, abrupt is a very relative word, and we'll talk about timescales a lot. It's important to keep that in mind. But so given the forcing, sort of we are concerned that if as a function of the forcing of the control parameter, if you like, there could be rather abrupt changes in different Earth system components, even if it wouldn't be abrupt in time because the systems are very slow, like the ice sheets. But still, if you plot that against temperature, for example, then it would still look abrupt, and that's what we mean by that. So are there subsystems that could show abrupt response? Which are the ones that we would consider most likely? And what would be the critical forcing threshold? So for example, what would be the critical levels of global mean temperature at which such a tipping event, such a crossing would be expected? And to look into the IPCC report again, from the summary for policymakers, I essentially only found these two statements. First is that abrupt responses and tipping points of the climate system, such as strongly increased Antarctic ice sheet melt or forest dieback, cannot be ruled out. And such a statement like cannot be ruled out, of course, you can say that with high confidence. Anything else would be rather funny. The second statement, the Atlantic meridional overturning circulation, the AMOC, is very likely to weaken over the 21st century for all emission scenarios. There's medium confidence that there will not be an abrupt collapse before 2100. And as you probably know, there has been a lot of debate recently on trying to predict a possible tipping time and to see where, like, what's the likelihood that it might happen before 2100. I'm a little bit, let's say, cautious in such statements because I think the uncertainties are still huge, but I'll come to that. So that was part one of my talk. Part two is just this one slide. From Greenland ice core records, I think that's the most convincing and compelling evidence that indeed the Earth's climate system is capable of critical or abrupt transitions. So what you see here is a reconstruction of temperature, almost annual. It's a really spectacular time series from Greenland ice core records, and shows you temperature, well, indirect, a temperature proxy, but just think of this as temperature for the past 120,000 years. This has been actually layer counted, so really so very precisely dated for the last give or take 60,000 years. And you see the entire evolution of the last glacier, and you see that this last glacier has been punctuated by these now on this scale that we're looking at, very abrupt temperature increases. These are called the Dansgaard-Oeschger events, after the two people who have discovered them. And I think the most extreme one was this one here, which was more than 16 degrees of warming of the annual mean temperature within a few decades. And then you had this gradual cooling. And I guess there is relatively strong consensus that these jumps in temperature in Greenland are in some way related to changes in the speed of the AMOC. Whether that something like this is then possible also in future climate. So we are somewhere here. That's of course a completely different question because the climate conditions are very different today from back then. But the key message here is, in principle, the climate system is sufficiently nonlinear to produce jumps like this. And of course, given that ecosystems, society, but also other climate components almost need time to adapt to change, such an abrupt jump is something in any sort of system, in any circumstance, it's something that we really would like to avoid under future anthropogenic climate change. The four systems that I'm going to talk about now concerning the risk of any future climate tipping are the Greenland ice sheet, the Atlantic Meridional overturning circulation, the Amazon rainforest, and the South American monsoon system. It is, of course, always sort of ambiguous what kind of systems you choose to look at. You can't talk about everything. There is maps, and you've probably seen maps with many more Earth system components on there than this one. It's, let's say, a trade-off between the sort of severity of the potential impacts if something would happen to one of these systems, and that's of course to some extent a subjective choice, sort of to what extent we are concerned that these systems might show a certain nonlinear or even abrupt response to the gradual anthropogenic forcing. So some trade-off between these considerations leads to this selection of four systems, and that's the ones I will now go through one after the other. I will start with the Greenland ice sheet. And so a key fact is that for any sort of critical behavior like abrupt transitions and so on to take place, the system needs to be nonlinear. There needs to be feedbacks, and typically we have sort of a balance of positive and negative feedbacks. So positive feedbacks are the ones that destabilize something, negative ones are the ones that stabilize something. For the Greenland ice sheet, and all of them act on very different timescales. So for example, the melt elevation feedback is probably on long timescales the most relevant one for Greenland. Basically, you have a Greenland ice sheet with surface roughly 3,000 meters above sea level. It's rather cold up there due to the atmospheric lapse rate. Then if you still get some positive degree days and you melt that surface, you reduce it in height. So you expose it to higher temperatures just because of the lapse rate. And then you accelerate the warming, and that's positive. I mean, that's a positive feedback, but it takes a long time to play out, like centuries to millennia. On the other hand, there's positive feedbacks related to the albedo. The uppermost snow layers, white snow layers, reflect the sunlight much better than the gray ice. There's also feedbacks related to snowline migration, the thinning of outlet glaciers, the refreezing of firn. On the other hand, there's negative feedbacks. the precipitation temperature feedback. So as the atmosphere warms, the water holding capacity increases. So there will also be overall enhancing hydrological cycles. So in general, more precipitation, hence in Greenland, more snowfall, so more accumulation for the ice sheet. And in addition, there's changes in the circulation patterns as the ice sheet height is reduced. It changes the winds regionally in a way that probably also leads to more accumulation, more moist air basically brought onto the Greenland, is it a continent? Onto Greenland. And so that's negative feedback, stabilizing ones. And we had this question, and I promised to talk about timescales. So we had this question, given that Greenland ice sheet, it's such a huge ice cube, and of course it won't react to sort of a few days or a few years of warm temperatures. And the question was, could we even surpass the critical temperature threshold that it might have, and that it probably has? Could we surpass that for some time? And if we manage to reduce temperatures in sufficiently quickly, sort of, can we get away with it? Is there a window of opportunity? And for this, we used two different ice sheet models. This is work by Niels, and had this idealized scenarios that you see on the top. So we have warming, and then we have cooling on different time scales, and used PISM and Yelmo for it. You see these, a lot of simulations for different target temperatures. And you see that there is there is a critical threshold. It's not the same for the two models. And you also see that you have to run these models for a very long time. So the scale on the x-axis is kilo years, because the ice sheet is so slow. And so using all these simulations, basically the motivation came from a paper that Paul Ritchie wrote some years back. A very nice paper that showed that if you don't have perfect timescale separation, then you can have indeed these overshooting scenarios where you manage to, so you cross the critical threshold, you cross the bifurcation point, and then depending on how fast you do that and how fast you revert temperatures back again, then either you get back to your original stable fixed point, or you collapse to the other one. But it's really a question of how quickly you revert your temperatures. And the question basically, this basically gives the whole story. And then, sort of, we needed to burn a few million CPU hours with the ice sheet models to basically come to a very similar conclusion. And that's then basically just the sort of summary plot for that. So depending on the model, there is a critical global mean temperature threshold for the Greenland ice sheet. It's somewhere between 1.7 and 2.3 degrees above pre-industrial. So still pretty much in line with Alex Robinson's estimate from 2010 or 11. And what you see here on the right is, so first of all, what you see is if you have a complete meltdown of the Greenland ice sheet, you have 7 meters of sea level rise. And maybe just as a sort of one take-home message, that's definitely something you don't want. But you also see that, so what you see here on the x-axis is the duration above that we spend above the critical threshold. And you see that if that duration is lower than 1,000 years, and you manage to bring the temperatures back below the critical threshold, then you're fine, more or less. You have, let's say, a maximum of 1 meter of sea level. Still not great. And of course, this is not supposed to just, the concern is still great, because reducing temperatures is orders of magnitude more expensive than stopping them to increase. So it just basically gives an argument against these doomsday scenarios that it's already too late. It still is a strong argument that mitigation should happen as quickly as possible and as much as possible. But then even if we cross temporarily the critical threshold of the Greenland ice sheet, there's a chance that if we manage to reduce temperatures, we avoid a full tipping of the ice sheet. So the question is, where are we? 1.7 to 2.3 degrees, that's the sort of uncertainty range from the model. It could, of course, be biased. It could be somewhere else. So let's go to whatever we have concerning empirical data, and try to measure the change in stability of the system, meaning try to measure if we have moved further towards a critical threshold or further away from it. And for that, there's a theory that goes back to work by Kubo and like around the fluctuation dissipation theorem and Wellen, and I mean, so in the 50s and 60s. Basically, what you have is a situation, or what you assume is that you are in a situation, and you have to assume that you are in such a situation of multiple equilibria. That's something you put in. But if that's the case, then you have these sort of two stable states, and to go towards a bifurcation means you're going from a potential well like this towards a situation like this, where the attained stable state is already less stable. The fluctuations can be larger because the restoring forces are weaker, up to the point where this stable state ceases to exist, and then the system necessarily needs to jump over to the alternative stable state. And that is sort of the tipping point, is the critical threshold in the control parameter, which is P here. That's the critical threshold that we cross, at which the transition will take place. And the idea is that we can measure from the natural fluctuations of the system. So let's assume there's weather fluctuations or so that drive the system, and these fluctuations, they will respond to any change in the basin of attraction and around the stable fixed point in a way that can be quantified. And I'm going to spare you the details here. So basically you linearize, well, just very briefly, you linearize around the stable fixed point. That gives you an Ornstein-Uhlenbeck process for those who are into stochastic dynamics. And that you can discretize, that gives you an AR1 process. And then for that, you can just look up in any textbook, you can look up the variance and the autocorrelation. And that's are the classical early warning signal indicators that have been used extensively in ecology and climate and many other fields already. Basically, the take-home message is, if you have very strong reasons to assume that there is an alternative stable state, and your system, there's a change in forcing, and your system shows increases in both variance and autocorrelation, then there is reason to concern that you might be approaching a tipping point. It's still no evidence, because you could still have, or still no sort of hard evidence, because you could still have situations where the variance and the autocorrelation increase for other reasons than moving towards a critical, like a bifurcation point, but we'll come to that. Applying this to the Greenland ice sheet, so there's these melt rate reconstructions from shallow ice cores in the Jakobshavn-Isbrae glaciers in the central western Greenland, and reconstructing heights from that. Indeed, you do see an increase in the variance and the autocorrelation, suggesting that at least regionally here, the ice sheet is losing stability, which would be then equivalent with saying, since there is an alternative stable state, according to our theoretical understanding, that the ice sheet is moving towards such a critical point. Now that would have impacts on the AMOC, on the Atlantic meridional overturning circulation, which is part of a global circulation system, the thermohaline circulation. And essentially what the AMOC does, it moves warm, salty water masses northward across the Atlantic Ocean. There they cool, and then you have salty, cold water masses that are relatively colder than their surrounding water masses, and that causes them to sink to deeper ocean levels, and then the water is returned to the south at the bottom, more at deeper ocean levels. And now there's a crucial feedback, the salt advection feedback, since the more salty water is brought north, the heavier the water there, and then the stronger the sinking. So that's an ocean circulation that operates due to a positive feedback. And now if we have a lot of Greenland ice sheet melting, we're inducing a lot of fresh water. There's other reasons too. There's the overall enhancing of the hydrological cycle in response to anthropogenic warming. There's the sea ice melt. There's the increased river discharge. But even there's also the discharge from Greenland ice sheet, and all that effectively lead to a freshening of this region south of Greenland, which might might affect this positive feedback and might lead to a weakening or even possibly to a collapse of this Atlantic Ocean circulation system. First, let's talk about what would happen if that were the case. So if the AMOC would collapse, so these are multi-model ensemble means for different seasons. It's work by Maya. So you see the impact of an AMOC collapse on the global precipitation. And so for the different seasons, and in particular, you see these significant decreases in precipitation in the tropical monsoon regions. So in the sort of boreal summer season for the West African, Indian, and East Asian monsoon, and for the boreal winter season in the South American region. Although in South America, in particular, like in this Amazon region, it's not as clear, because you do have a decrease in precipitation in the northern parts, but you do also have an increase in precipitation in the more southern and more eastern parts of the Amazon. This is something that sort of from model version to model version, this line here between the positive and negative anomalies shifts and moves. It's highly uncertain. Currently, we believe that a collapse of the AMOC would probably have a stabilizing effect, at least on most of the Amazon. This is just a sort of like a small interlude. This is work by Nyanda from PIC, where she superimposed the information or the data from an AMOC collapse from the North Atlantic housing map that was led by Laura Jackson, and superimposed that on an extreme SSP 8.5 scenario. These are the precipitation anomalies resulting from that, and the temperature anomalies. And so what you see here is, so you only global warming just due to the increase in temperatures, the transitions. So in red, we have forest to savanna transitions. In orange, we have forest to biostable, so sort of mixed state transitions. And you see, as we increase the temperatures from 1.4 above pre-industrial to 2.3 to 2.8, most of the Amazon rainforest will disappear according to these projections, because there's not sufficient rainfall and the temperatures are too high. Whereas if we add the AMOC collapse, eventually that will also happen, but it will be delayed considerably due to the increase in precip in large parts of the Amazon due to the AMOC collapse. All right. So as you probably know, unfortunately for the AMOC, we don't really have observations. We have observations starting in the early 2000s, and that's just a blink of an eye for such a system. So to sort of get an idea of AMOC evolution over, let's say the last century or maybe 150 years, a lot of different so-called fingerprints from sea surface temperatures or salinity have been proposed. And so I'm showing you just the trend in sea surface temperatures and in salinity concentrations over the past 100 years. Trends in particular for the sea surface temperatures are essentially positive everywhere. That's just global warming, apart from a region south of Greenland, which is the subpolar gyre region, and possibly and also the region where we sort of think that the AMOC brings the warm water masses from the south. So this cooling south of Greenland has been suggested to indicate a slowing of the AMOC, although that's not beyond debate for now. On the other, so something similar you can also see for the salinity. So there's a suggestion that the AMOC has been weakening, and there's also proxy evidence that it might be weaker than it had been, at least in a 1,000 years. But of course, all of that comes with a lot of uncertainties. Looking at the different fingerprints, so basically you see these boxes and then you average sea surface temperatures or salinities, subtract some global mean or northern hemisphere mean. There's many different fingerprints. Here you see 4 based on SSTs and 4 other ones based on salinities. And most of them show a slight decrease. And back then, I asked myself, so is this apparent reduction in AMOC strength just a linear dumping, something that I wouldn't be particularly concerned about? Or is it actually a sort of moving towards that critical threshold that conceptual models suggest are there, and also nowadays some comprehensive models suggest that we have this sort of bistability in the AMOC. But again, something that is still debated. To answer this question, I used critical slowing down, actually a slightly refined version of that, because as I said earlier, we can have these situations where the autocorrelation or the variance increase for other reasons than approaching of a tipping point. and so developed this alternative indicator, and this is part of a lot of work that we have done since then, with Chris Butner in particular and Andreas Mohr, to get improved early warning indicators that are less prone to false positives. And so in this case, what you see on the right is a linear model. By construction, it cannot exhibit tipping. And you just increase the autocorrelation of the noise that drives the system. And that increase in autocorrelation of the driving noise leads to both an increase in the overall variance and to an increase in the autocorrelation of the system itself, producing these beautiful early warning signals without anything actually happening. So nothing, I mean, sort of this system can't even tip, still you get early warning signals. So that's a problem, of course. And then you rather would like to have an estimator that more directly focuses on the restoring rate, on this linear restoring rate, in a way that is not sensitive to changes in the driving noise. So you do a different kind of regression where you leave you admit correlated noise here with changing correlation strength. And then you get an estimator that in this situation where it shouldn't react, it actually does not react. It just gives you a straight line. It does not increase. Whereas in the situation where you're actually moving towards a critical transition, it still reacts in the way that you want and gives you a warning. So this I'm now throwing at the fingerprints of the AMOC. First, globally on the spatially resolved SSTs and salinity. And so you see the North Atlantic for the SSTs, everywhere where we have stippling, you have significant increase, meaning a stability loss. And for the salinity, it's along this pathway of the North Atlantic drift and then towards the Erminger Sea. So that is already gives reason of concern that there might actually be some kind of destabilization going on. Then again, looking at this for the different fingerprints of the AMOC that had been proposed previously in the literature, there is so there's strong agreement that lambda, the restoring rate, the negative restoring rate has been increasing, suggesting a stability decline on the course of the last 100 years. However, there's one thing that I did not pay sufficient attention to back then, but then luckily Maya joined our team and did pay a lot of attention to this. The data is highly uncertain. So there is, of course, massive uncertainties in the representativeness of these fingerprints for the actual AMOC, but there's also uncertainty in the SST or salinity data themselves. You can imagine that, early 20th century, how did you measure sea surface temperatures or salinity concentrations in any depth somewhere in the Atlantic Ocean? The data coverage, you see this here for different regions and for different data sets. Note the exponential, the logarithmic scale on the y-axis here on the top right. So the numbers of observations has increased exponentially, but it also means that it had been extremely low in the earlier parts of the record. And then the gap filling and reconstruction that needed to be done to get complete spatial coverage, of course, induces biases, in particular in the variance. So in these cases, the variance should definitely not be used with all these fingerprints. Don't use variance as any sort of indicator for stability change. It's most likely, if you see changes in variance, is just due to non-stationarity in your data that you can trace back to the way how the data had been processed and had been gap filled and so on. So we focus on the restoring rate lambda, which is much less sensitive to these data set pre-processing. Still, you have uncertainties. You have uncertainties in the original data, and then Maya can propagate them to the actual stability indicator lambda. So you see these green or turquoise shadings. And the take-home message here is that even propagating all the uncertainties, the qualitative statement that there had been an increase in the restoring rate lambda, meaning a stability decline, that is robust, that remains significant. And we tested this very thoroughly. However, if you look at this and then, no matter how sophisticated your technique is to sort of try to extrapolate this into the future to see when you might have when lambda might hit 0, that's where we expect the tipping point. if you consider these uncertainty ranges, then you can already see how any way, I mean, no matter how well you do it, any extrapolation of this into the future will be subject to extreme uncertainties. And so this is a summary plot doing the probably pretty much perfect method that Peter and Susanne Ditlevsen developed for this extrapolation, but then doing it and incorporating all the uncertainties in the underlying data, and also looking at different proposed fingerprints, which of course aren't exactly equal. Then we get a range of at least, let's say, the year 2000 to 5000. If you use all ensembles of the different reconstructions and analysis, it's actually 2000 to 8000. So we get a range of 6000 years for any tipping, with a predicted tipping time. And that's always under the assumption that the system tips. So the method does not work in a case where actually tipping is impossible. It would still give you a tipping time. So even under the assumption that there will be a tipping that is in the future, then the range of uncertainty gives you basically 6000 years, which I would say is then not really a prediction of a tipping time anymore. To sort of sum this up again, so what's the problems with anticipating critical transitions from observational data or from empirical data? So in principle, you can think of it like, on the one hand, you have a dynamical process, some true physical variable x, and that follows some kind of stochastic differential equation like this. And then you have a measured observable, which is a function of x, but then you add more noise. So you have lots of noise due to the stochasticity in the system itself, but then you also have uncertainties in your measurements, and you're probably reducing your dimension drastically, brutally. So let's say AMOC, you know, we were looking at the 3-dimensional ocean circulation, and what I did here was reducing that to 1 dimension. And I mean, I didn't justify that in any way, I just did it. So we have a lot of assumptions and a lot of possible sources for problems that go into this theory. And I'm not going to go through all of them. The slides will be online, and the talk will also be on YouTube. So, but so maybe some of the more crucial ones are the assumptions on the noise driving the system, whether that is white in time or correlated, whether the variance of the noise is constant or changing. Then I'm actually rather concerned about this fact that sort of this D could be very, very large. So X is a high-dimensional system. And then we are actually looking at a much, much lower dimensional sort of representation of the system, where the question is, does it sort of inherit all the properties that it needs to have this sort of whole stability analysis be meaningful? And then there's questions about the consistency in the measurements, whether the measurement noise is stationary. It's certainly not for most of the variables that we've been looking at. I already showed you the example of the AMOC, and I'm going to show you another example where it's not. Yeah, so to sort of test a little bit, to be able to test a little bit better if this is possible, we focused on vegetation, because globally gridded vegetation, we have a lot more instances. We have a lot, we actually do have transitions, so we can test the theory. We can test in particular whether the restoring rate estimates that are based on the variance or on the autocorrelation, if the theory is right, then they should coincide. If the theory does for some reason not work, so if any of these assumptions are broken, then the estimates shouldn't be expected to be the same. You see here for different land cover types. So if you have evergreen broadleaf forests or closed shrublands, makes a huge difference in the reliability of this critical slowing down theory. So generally, unfortunately, at least for these optical and very widely used data like the normalized difference vegetation index, it does not work in any closed sort of very dense vegetation cover, which is unfortunate because that includes the Amazon rainforest, it includes the African and the Southeast Asian rainforests, it includes the boreal forests. So all the stuff that we're interested in, because that's sort of where we're concerned, we can't really use critical slowing down theory, at least not based on optical satellite data, because the theory just, I mean, it doesn't make sense. On the other hand, there is vegetation optical depth, which might be more promising. It's a microwave data set. And there, what we did was we actually looked at transitions induced by fires and the recovery, so we could infer an empirical recovery rate from them, and then compare that to compare this empirical recovery rate to the theoretical estimates based on autocorrelation and variance, and actually overall got a pretty good result. So that did confirm for VOD, for vegetation optical depth. It did confirm the applicability of the critical slowing down framework to some extent. So you see here, so the green line should always sort of sit within the gray shading for it to work. So this works well here for the variance. Not perfect for the autocorrelation. Still, the monotonic relationship between both is okay-ish. And then you also get this result that the restoring rate is lower, meaning the vegetation is more resilient, more stable if you have a water surplus than if you have a water deficit. That's sort of like a physiological proof of concept for this. And this is true for any different plant cover type that we looked at. Now, looking at trends of the VOD resilience estimates computed from VOD, the Amazon does have roughly 75% resilience loss. And so there's a lot of different feedbacks that play a role for the Amazon rainforest. If you just plot the tree cover fraction versus the mean annual precipitation, then you get a scatter plot like this. So these are the rainforest parts, and these are the sort of degraded or savanna-like parts. And you see that for the same mean annual precipitation, it seems that both the rainforest state or the savanna-like state are possible. There's caveats to this that I don't have the time to talk about, but this could, I mean, there could be different reasons than actual multi-stability for this sort of bimodality. But let's assume that there is the potential for a critical transition between the rainforest and the savanna-like state. And then if that's the case, then using different estimates of the vegetation optical depth, either a multi-sensor product, where again you have non-stationary data, so that's problematic for the critical slowing down theory, but then Lana did a very thorough check if that's actually also, if you also see the stability decline, this resilience loss for the Amazon in single sensor products where you don't have any non-stationarity due to measurement processes. And indeed, she could confirm the results that originally Chris Bolton found for the Amazon, that there has been an ongoing decline in resilience, which is stronger in drier places, as you might expect, but which is also stronger in places that are closer to humans. So just look at the trends and sort of, I mean, separated, this is sort of very close to humans. This trend is stronger than if you're far away, like 150 kilometers to 200 kilometers away from humans. And that motivates my last final short bit. I'm out of time, but give me 2 more minutes to talk about the South American monsoon, because so the land use change and the resilience loss in the Amazon, the potential degradation following that, has impacts also for the South American monsoon. And this you can model this moisture exchange between the atmosphere and the rainforest. So there's basically a continuous exchange of moisture through evaporation and precipitation. And there is a positive feedback in the system. That's, I mean, it's technically a monsoon system, although slightly different in functioning from the Asian monsoon systems. And so for this monsoon system to work, you need a lot of moisture over the South American continent, over the tropics. And then the concern is that if you have too much degradation of the Amazon rainforest, you're effectively reducing the evapotranspiration. So you're reducing the amount of moisture that is fed back into the atmosphere from the soil in the eastern parts in particular. And then overall, there will be less moisture in the entire over the entire basin. Maybe to a point where you make that positive feedback that enhances the gradient, the heating gradient between ocean and land, where you collapse that feedback, and then you have a significant reduction in rainfall. And in simple models, this is how it would look like. So you have the number of deforested boxes here, and you have the precipitation in change in percent in the most western part of the Amazon. And this actually follows a double-fold bifurcation. And then in the model, of course, it's easy to find, because it's a double-fold bifurcation, you see this critical slowing down signals, and the question is, do you see those? So basically guided by these insights, Niels looked at observations and like reanalysis data, to be honest, and also along the main moisture transport routes of the South American monsoon, did find very clear increases in autocorrelation, suggesting a loss of stability of the monsoon. And likewise, there's also physical precursor signals or warning signals for a collapse of this coupled system that come from an increasing dry season length that has been, I mean, we just confirmed many other papers that had already reported this, but it's also predicted by our model and also predicted by the model and confirmed in reanalysis data as a decreasing soil moisture. So to conclude, and sorry for taking a few minutes longer, so both theory and paleoclimate data suggests the possibility of a critical transitions in different parts of the Earth's climate and ecosystems. And the sort of looking into the empirical data that we have, it seems that the stability of some major components of the Earth system has declined in recent decades, although it's important to emphasize that the uncertainties are huge and predicting potential tipping times is subject to these uncertainties and hence rather problematic. Oops. Yeah, and basically all the open questions that are sort of now left, that's what we're going to try to answer in the coming 3.5 years in ClimTip. And with that, thank you very much for your attention.
Thank you so much, Niklas, for this amazingly comprehensive talk. Let's see if we have questions from the audience, questions of comprehension or any specific research related questions.
You want to go ahead?
Yeah, so Niklas, thanks for the great talk. And I was wondering about I wanted to ask about this prediction, these predicting the tipping times. So you've done this exercise with Maya Ben-Yami on the AMOC, right? But do you think for some other tipping elements this might be more promising? So applying Peter Ditlevson's method, and then the systems where we have much more data, maybe better data?
So I'm going to say I have very little hope, but I'm absolutely happy to be corrected with that statement. But yeah, I have very little hope because I don't think that for, let's say, at least these global scale tipping elements that we're talking about, like Greenland, like Amazon, AMOC, maybe monsoon systems, coral reefs, I think that, so first of all, the data coverage isn't great for any of them. It's actually rather poor. The time scale that we have for which we have coverage is usually, I mean, for Greenland, it's ridiculously small given the sort of intrinsic time scale of the system. That's one problem. Then the further you go back in time, you always have these non-stationarities in your data coverage, leading to non-stationarities in your data due to the way that they are reconstructed. So from observational data, I would say you will always have a problem. And maybe sort of the best hope should be something like somewhere, for the Amazon, you have nowadays great observations from satellites, but then again, you have serious uncertainties in what the satellite measurements really mean in terms of physiological variables, like vegetation optical depth. I mean, it sounds like something vegetation, but it's really just sort of microwave scatter that is somehow measured, and to what extent that really reflects biomass and not just soil moisture and so on. It's all very, very open. So I would say based on observational data, I'm rather skeptical. And then of course there's the additional problems that you have to make assumptions, mechanistic assumptions. And so what, for the AMOC, Peter's assumption was to use a simple saddle node bifurcation as the sort of model to extrapolate. And then sort of given the AMOC as a 3D ocean circulation system, to what extent that is well represented by a saddle node normal form, I don't know.
Do we have any more questions? I think any in the chat. I thought that you were going to cover the West Antarctic ice sheet as well today.
I know very little about the West Antarctic ice sheet. Certainly much less than I would need to know to talk about.
Sorry.
But actually, I mean, as you're bringing this up, I think we should have a talk, or like, I mean, several talks maybe dedicated on the ice sheets. I think that would be fantastic, because we have a lot of experts in the team.
Right. I was just wondering, in terms of the communication, the 5-meter sea level rise, for example, or the 7-meter sea level rise from the Greenland, this is the extreme case, right, of like full melt. But even before we get there, sea level rise, it seems so abstract and so small, kind of. How would you maybe help to understand that, you know, scale on a more concrete example?
Yeah, that's I mean, sort of, that's always the question, sort of like numbers can feel large or small, right? And even sort of more conservative estimates of like, without any instabilities, 0.5 meter of sea level rise until 2100, people might say, yeah, but I mean, 0.5 meters is not even 1 meter. But if you ask, you know, people who build dams and dikes and things, and sort of, I mean, if you ask people who do coastal planning, or if you ask the mayor of New York or so, they probably tell you a different story, because that on average that comes on any sort of extreme sea level like sea level height you know, event. This comes on top, and I think that actually even 0.5 meter of sea level rise is really very problematic.
Okay. And if there are no questions, perhaps was there anything else that you wanted to go into more detail that you had to skip earlier in the interest of time?
I think I mean, maybe sort of, I mean, so one thing that is, of course, still very interesting is to sort of try. So I mean, I made this point that we can't predict tipping times at this stage based on observational data, but of course, that doesn't mean that we can't do that categorically. I think still that there is scope in improving our models and sort of, you know, sort of our process-based physical models. They're not currently designed to do these sort of predictions of tipping times or so, but I think that so one of the key tasks ahead of us is, I think, is to get a systematic understanding of critical thresholds in global mean temperature in land use change for the different tipping elements. And then we will see after, I mean, sort of, this is of course part of the great work planned and already started to be carried out in TipMip. And I guess so I'm expecting that the uncertainties in our estimates of critical temperature thresholds and so on, if done right and if done thoroughly, the range will be huge. The uncertainty will be very large if the estimate will be done right. And that is, of course, something then that we want to reduce. And for that, we need better models. We need better ideas how to constrain the models with the observational information that we have, maybe with emergent constraints and so on. So I think that's one of the main tasks ahead of us, is to get better estimates of these critical forcing thresholds, combining observations and models in a good way.
I just had one more question for myself. Like now I'm like delving into all of this science around climate tipping points, and I find, I mean, I don't know, it's hard for me to reconcile, for example, these two recent papers, right, which you both were involved in. One was Andreas Moore, which was kind of about the possibility of more clearly having an early warning signals. Yet on the other hand, this other paper with Maya was about not being able to predict tipping points. How do you reconcile those?
Maybe the problem comes from an unfortunate choice of unfortunate naming of these things in the first place. So I'm not sure it was a good idea to call the variance or the autocorrelation or the more refined indicators that I or then Andreas, and Andreas probably now at the moment, that's probably the best indicators we have. I'm not sure it was a good idea to call them early warning signals in the first place, or early warning signal indicators or whatever. They are measures of critical slowing down. They are measures under certain assumptions. They are measures of changes in stability. And then under more assumptions, then they might be used to anticipate forthcoming transitions. But I don't think that they should be misused as sort of predictors. They don't predict things. And then also the apparent sort of, you know, the sort of, there's nothing to reconcile then, I think. Because it's basically like you should not, and I think, I mean, there's very rare cases in science, I would say, where you should just take historic, like any sort of information from historical data and then in some way just extrapolate that in the future into the future. And then as long as you don't do that, then it's not a prediction. Then it's just sort of a statement about how stability has changed in the historical record.
Mm-hmm. And then in that case, what would be, since the project, for example, for us, one of the kind of aims is to look at the possible early warning systems, what would that be then? What kind of indicator would be called that?
Sorry, I didn't get the question.
Like, I think ClimTip, right, as part of our aims, early warning signals is part of the kind of the objectives to kind of clarify.
Yeah, that's of course then, you know, once the terminology sort of sticks, then you have to work with it even if you don't like it. But I would still sort of, when I say early warning indicator, I still mean a critical slowing down indicator and sort of don't expect it to be helpful in really predicting things.
I see. Okay, thank you.
There's one question in the chat by Casey, whether the restoring rate parameter had been calculated for CMIP6 projections. Yes, recently it's but it's a Earth System Dynamics discussion paper. So you can, I can put the link in the chat in a second. And it's rather inconclusive. So I mean, for sure we do not confirm what we see in observations, but we also don't see a lot of false positives in the CMIP6. So basically, one take-home message is that it's not likely that what we see in the observations is just sort of is a false alarm in the sense of it just arose by chance. Sort of taking all the CMIP6 models as a, I mean, you know, this is statistically not clean, but sort of taking the CMIP6 models for like a null hypothesis, it's not likely that what we see in the observations or in the observation-based data for that to arise by chance. But the models also don't seem to be in a place where they are right now capable of sort of even predicting the historical trend in the AMOC as far as we think it looks like from the fingerprints.
Okay, I think we are out of time. Thank you so much, Niklas, for your super interesting talk, and also thank you all for joining, and see you next time.
Thank you, Quad, and thanks Sebastian for posting the link.